In the summer of 2024, many of the world's leading physicists gathered at the Black Holes Inside and Out conference to discuss and debate amazing new discoveries that could revolutionize how we understand the universe. In this film, we'll meet the astronomers and physicists who attended the conference and will shape the future of gravitational physics for decades to come, a field which had long been overshadowed by the dominance of particle physics.
There's a feeling that gravitational physics is the future for the next 100 years. There's also this feeling that particle physics is almost exhausted. It's a beautiful thing. For 50 or 70 years, it gave us a new world, but we just don't have the resources to go after higher and higher energies on our planet. And so the feeling is, and there's several beautiful ideas, let's not use our planet. Let's use the cosmos. It's a beautiful generator of high energy physics. And we see it when we look at black holes, at neutron stars, high frequency gravitational waves. So it's all in gravity. Gravity is giving us information about particle physics, high energy physics, and gravity itself. So yeah, I think I certainly feel it. I feel I'm the new thing. We're all rock stars here. And you see it also just by the sheer number of PhD students that speaks a different language so easily and that are so excited about doing this.
Gravity has moved into center stage. I mean, previously, even in the 80s, right, 70s, 80s, people didn't particularly believe that gravity is going to be important. There are these compact objects, but still, most astronomers actually did not believe that they were black holes or they were so ubiquitous. And so now, yeah, it's completely changed.
I mean, as always, one of the nice things about a conference is you hear about things that you never heard. You didn't read the papers. There are so many papers out there. Being able to get together with people, talk to them, hash out arguments, disagreements. You might not get rid of the disagreement, but you at least understand the other person better.
It's more exciting because finally we have a lot of data that are more than we were hoped for only a few years ago. I think the breakthrough with gravitational waves and also the Event Horizon Telescope really changed the game.
The Event Horizon Telescope, or EHT, combined radio telescopes around the world to image the shadow of supermassive black holes billions of times the mass of the Sun, with a resolution so high it could see an orange on the surface of the Moon.
We're working for many years with calculation, model and other, and see something concretized, and to me was like a born of a baby, because our idea, the idea are inside us, like when you have a baby, but take more time. So to me was something that I will remember forever.
The image EHT took made headlines around the world. But it's only just the beginning.
We are planning to improve our radio telescope, our array of radio telescope. We started also constructing one in Namibia, and we are collecting other to improve our sensitivity. But also we want to have a space radio telescope, and this will allow not only to see like now to see an orange on the surface of a moon, but we can see the detail better, the detail of this orange on the moon. So will be amazing.
EHT came on the heels of yet another monumental breakthrough in black hole physics, the discovery by LIGoO of gravitational waves, ripples in the very fabric of space and time arising from black hole collisions. It was the culmination of decades of work, overcoming doubt that such phenomena even exist, let alone could be detected.
I started off in the 1970s. Black holes, most astrophysicists thought that was just one of these dreams of the general relativists, and who knows what in the world they were talking about. And yet, more and more evidence was coming that these might actually have physical importance, quasars, etc. Discovery of sources out there which could really only be explained by those things being black holes being out there. And then, of course, the gravitational radiation was discovered after people had been working on it for 70 years. I mean, Weber got started. He thought he had seen gravitational radiation. Nobody believes now that he did. But suddenly people said, maybe it's possible. You got more and more people excited. So yeah, certainly general relativity and the things attached to it have definitely increased in importance in the field and excitement.
The treasure trove of LIGoO's information comes in the form of a ringdown signal, essentially how the vibration of space-time relaxes back down like a bell going quiet after it's been rung. But so far, LIGoO has only seen a fraction of the modes of vibration that are believed to exist.
So currently LIGoO is taking data, but it will improve by a factor of 2 to 3 over the next 2 to 3 years. But after that, there is another improvement coming along. It's called the A-sharp detector, which will improve it by another factor of 2. But that's not enough. In order to see all these modes, about 20 years ago, we showed that we need to have detectors that are 10 to 100 times more sensitive than where LIGoO is today. And that's where we are building what is called Einstein telescope in Europe. I led this effort for many years when I was in Europe. Now, after moving to United States in 2016, I've been leading the science case for what is called a cosmic explorer detector, which is a 40-kilometer arm length detector instead of 4 kilometers by 4 kilometers. So it's 10 times bigger. And that is the one that will be able to observe all these higher modes and confirm that the black holes that we are seeing are truly the solutions of Einstein's equations and not some other exotic compact object. But to me, discovering these alternative objects is what the most exciting thing about, discovering what else is out there. Is it only black holes or are there other compact objects? This is what we want to observe with the Cosmic Explorer and Einstein telescope.
To see what these alternative objects might be, click on the link below for our film on black hole alternatives.
Einstein telescope has something like 5 to 8 years lead time compared to Cosmic Explorer. In the US, the National Science Foundation was not going to consider next generation observatories until a detection was made. So we studied Einstein telescope starting from something like 2008. But the Cosmic Explorer one started only in 2015, 7-year lead time. We have shortened some of that, but I think Einstein telescope is going to decide over the next 2 years already which site. They already have many sites, which site. Whereas Cosmic Explorer is just identifying how many sites are there. But we are not deciding that. That's probably about 4 years down the line. So Einstein telescope has also assurance from Netherlands of money to build one detector and partial money from Italy to build a detector. They're now exploring whether there's going to be only one site for Einstein telescope or 2 sites. This is something that's still going on. When you make an instrument that is so much more sensitive, we don't know what we are going to detect. And I'm really looking for many, many discoveries. Over the next 3 to 4 decades, there'll be explosion of research in this area.
The next decade will also see the launch of the world's first space-based gravitational wave detector, LISA, with arm lengths a whopping 2.5 million kilometers long.
LISA is going to see the entire visible universe. It's going to see black holes that sit at the center of galaxies, supermassive black holes. And we hope that LISA will see new physics, gravitational waves that come from the Big Bang. It might even see new, we call them fundamental degrees of field, of freedom, new scalar fields axionic fields that might solve the dark matter problem.
There's been a lot of activity in terms of using black holes as detectors of light fields. So the idea is that there might be light fields that exist in the universe. Dark matter could be a light field. So it's a quantum field, which like a magnetic field, but electromagnetic field is massless, photons are massless, but there could be other fields in the universe, exotic ones that we haven't detected, but they could be responsible for dark matter, dark energy, or other properties of quantum physics. And black holes could amplify them. So that's been a kind of a topic that's been, people have been interested in it for the past decade or so, and there have been a lot of talks here about the detection of these light fields by black holes.
One thing LISA will resolve is the so-called Hubble tension, dubbed the biggest crisis in cosmology, and is related to how we measure the expansion rate and so infer how much time has passed since the Big Bang.
We have two methods. One is called distance ladder measurements through supernovae and standard candles. They measure this. But there is another method which is also very precise, and it's kind of based on the inference on cosmic microwave background. And there we know if universe expands differently, then the way the anisotropies of the temperatures would look like, their statistics would be very different. So you can also measure this parameter through those measurements. And these two, for example, do not agree. So there is this term more recently used called the Hubble tension, because why these two measurements do not agree with each other. What is exciting is these black hole mergers and the gravitational waves they emit to us, they also provide a new way to measure distances, and it's often called the standard sirens as opposed to candles. Because first of all, they're more direct. They're not based on distance ladder, so you don't have to use other methodology in local universe to kind of measure what's the distance to this and therefore to distance to the other object and so on. We call them sirens because it's kind of like sending sounds to us. So as opposed to light, gravitational waves in a way are waves of the medium, which in this case is space-time itself. Using those measurements, then we can again go after the cosmological parameters and evolution of the cosmos, how fast it's expanding, what happened in early time.
But resolving the Hubble tension is not the only gift future gravitational wave detectors may give to cosmology.
If we learn something about, let's say, quantum gravity close to the black holes, then we can take it back and apply the same thing to early universe and see what happened there. So these two are complementary in that way. But there is more, because there could be, and in this particular conference, for example, we heard talks about it, there could be other types of black holes that were formed very early on in the universe. And now that we have this window of opportunity of observing signals and gravitational waves, one of the hopes is that in future we might be able to go after observing those signals if they exist. It's a different kind of detector, different frequencies. So if observing early type primordial black holes by itself also tells us a lot about the phenomena that happened back then, what kind of physics existed, what scenarios are viable.
LISA works in the low frequency bands, right? It sees low frequency gravitational waves. But we have to remember that since the last year or two, we know we can also see gravitational waves in the very low frequency band. We have an array of pulsars, the PTAs, that see very low frequency gravitational waves. And these are also suited to observe pairs of supermassive black holes when galaxies merge, or gravitational waves from the Big Bang. So in fact, one of the hot discussions in this meeting was, where should we go? If we're given infinite resources, what detector should we build? And some of us are divided between the decihertz window, which is not well covered neither by LISA nor by the current Earth-based detectors, But others think, we're just blind people. We don't know what's out there. We're not God. So maybe we should just move away from where we're looking now. Why don't we go to super high frequencies? Maybe there's an entire new universe out there in the megahertz or the gigahertz gravitational wave regime, in the same way that there was a new universe for standard telescopes, right? X-ray physics, gamma ray physics, as contrasted to infrared physics.
Current gravitational wave detectors use lasers to measure the change in length of the arms of the detector. Such a device is known as an interferometer, but scientists are now considering an entirely new type of detector that uses atoms rather than lasers.
Well, atom interferometry really uses the wave-particle duality, right? And it builds on this idea that that you can build quantum, almost macroscopic systems that obey the laws of quantum mechanics. You can place large systems in a single quantum state, and that's very sensitive when it interacts with an incoming gravitational wave. It's super fascinating technology. It will be built on Earth. We're talking about condensed matter physics. I can also easily imagine then that 3-4 decades from now, we are going to be able to place these guys in space. But there's other options for this, right? We know we don't even need condensed matter to go after high frequency things. I have to remind all of us that when we started building gravitational wave detectors, these were bars. And we are going back to the idea of bar-like detectors that are sensitive to a narrow window, but they are very sensitive to a narrow window of frequencies. And just now, we also heard about a huge ongoing effort to actually place a detector on the moon. And one idea is to use the moon itself as a detector. The moon is it's a satellite. When a gravitational wave would come, the moon would oscillate. We would see seismic waves, and we would be able, if we're sufficiently clever, to understand the properties of the wave from the way that the moon oscillates. Other alternatives are to place optical cables on the moon. We still need to understand very precisely the seismic activity on the moon, which we don't. But you see, there's all these, they look like dreamy detectors, but we're thinking about them. We are going to make them.
But not every new detector is as grand as building arrays in space or on the moon.
You can test the superposition of space-time in the lab. And this is thanks to the fact that we can keep in a superposition, so in a quantum state, objects that are more and more heavy and for a longer and longer time. So this allows to witness superpositions of space-time, and the way in which we see it is the fact that the particles that we can measure may have some features that are crucially dependent on the fact that the entanglement that they carry has been generated through a gravitational interaction. So this is great. It would be a possibility to check the quantum property of the gravitational field in the lab, possibly available even in 5 or 10 years. We can use the same setup, possibly to detect small black holes, small remnants. We can see one of those objects passing through the detectors. So this is something that could be done in principle, and it's a technology that is definitely available to us. It's exactly the same thing as it was explored for dark matter detectors, except that before people were looking for a kind of particle that was much lighter, while here we are looking for a particle that is a Planck mass particle. So usually think Planck mass is something small, but in the case of a mass, it means a macroscopic mass with respect to the standard particles that we consider. With respect to particles, this is very, very heavy. And that's why this is also a very efficient way to have dark matter, because you need just a few of them.
Progress is not just happening on the experimental side, but also for the theoretical. In particular, many participants were excited about a talk from Mihalis de Fermos that undermined what's been called the third law of thermodynamics.
So black holes are thermal objects. That's why they evaporate. And that means that they satisfy the 3 laws of thermodynamics. That's the expectation. And, there's the first law of thermodynamics, second law, the very famous one, entropy increases. And then there's the third law of thermodynamics. And the statement of the third law of thermodynamics is essentially that there's no finite number of steps that you can take to reduce a system to 0 temperature. And so far, it looked very much like a black hole satisfy that particular law. And that's part of the consistency of black hole thermodynamics. And I should also say, a lot hangs in the balance of black hole thermodynamics. Almost everything we understand about quantum gravity these days has its origin in some way or other rooted in black hole thermodynamics. So we really think that statement is true as a statement about quantum gravity. Mihalis reviewed a very interesting paper which found that within classical general relativity, it is possible to violate the third law of thermodynamics for black holes. So it is possible to create a black hole and then through a finite number of steps, a finite amount of time evolution, get it to the point where it has 0 temperature. And as a physicist working on black holes, that's very disturbing, because if black holes are a thermodynamic object, then they shouldn't be violating the third law of thermodynamics. Now, you could say, okay, well, thermodynamics is kind of about averages. Maybe this is just a very atypical situation. But, Mihalis explained this paper, and it seemed to me that you could sort of do many different iterations or variations of this thing and still get it to violate the third law of thermodynamics. And so then the question becomes, does something happen that's dramatically different once you start adding in quantum effects? Because if you allow yourself to consider the possibility that these black holes live in a universe where you have protons and electrons and other things that interact in a quantum fashion, does that sort of prevent the black hole somehow from doing this finite process that gets it to 0 temperature? And there was an interesting discussion with Roberto Emperan, who suggested that yes, this must be the case. It would be fascinating to know if that really happens, or if somehow there's another constraint or something else going on in quantum gravity that enforces the third law, or possibly that the third law can really be violated and black holes as thermodynamic objects behave a bit differently from ordinary thermodynamic systems.
There's a third law of thermodynamics that kind of says you can't get to absolute 0 temperature. I've never understood why that is considered to be a law of thermodynamics. I mean, and, so I don't think it belonged in the laws of ordinary thermodynamics, and now it is definitely not part of the laws of black hole thermodynamics, but I think everything is fine.
These results say that the so-called third law of black hole mechanics that was proposed by Hawking, Bardeen, Carter, and Hawking is not true in general relativity. They have proposed this law, which is not true in general relativity. But there's a very, very interesting exchange between the foremost and somebody coming from string theory community, but more let's say quantum field theory community. And clearly there's such different viewpoint up here, because point of view of the foremost was, look, I mean, I'm working with classical general relativity, and classical general relativity, this is a fact. So there's a very interesting head-on collision, because people come from different communities and they think only in one way, right? I mean, and there's no really intellectual difference between what they're saying, but somehow it looked like they were strongly disagreeing, because Roberto Emperan, who's coming from quantum field theory side, he said, no, near extremality quantum physics is very important. So you cannot really, we know from thermodynamics quantum theory is important. So this is really not telling us really anything about the real world. It's not, etc. And his point was that, well, I'm talking about black hole mechanics. But the trouble is that they kept using terminology that, that just was very, so it was very interesting.
Resolving these sorts of disputes may require us to go beyond general relativity by listening more carefully to black hole collisions.
They have proper sound, like a guitar or a piano string, and we realized we can do an immense amount of things by listening to them. We realized we can measure their mass, how much they spin, and we can even test general relativity. So this is a hot topic because a year ago, we also realized that we can go beyond the traditional sounds. We can listen, we call them nonlinear modes. It means we dig deeper into Einstein's theory. So we're still now trying to understand how much we can go into this effort, but it's something clearly that will play out for the next 10 years or so. The other thing that's been hot for decades is testing general relativity. And I think the consensus now is that it's becoming a mature topic, and we need to understand what alternative theories, what theories that go beyond Einstein we should focus on, and why. It's really important we understand why we study specific theories if we know that they are not the answer to puzzles like dark matter, dark energy, and so on. So we're now trying to focus our efforts and to understand better how we're going to split tasks. And finally, and to me this is still the big thing, it's clear from this meeting that quantum effects, marrying quantum mechanics to classical general relativity, Einstein's theory, is still very much an open issue. We don't understand the interior of black holes, and we don't even understand if this ignorance is going to play a role in the exterior of black holes. We don't know if it causes a measurable change in the exterior. And this comes back to the sounds of waves, right? If you take a box with a gift inside and you shake it up, you more or less have an idea of what's going on inside. This is what we're trying to do by listening to black holes. Perhaps this characteristic sound of black holes will inform us on how we need to correct general relativity on the interior of black holes. It's a very exciting time.
Another interesting direction is the connection between quantum mechanics and gravity, the so-called holographic conjecture or holographic principle. So the idea is that a theory without gravity on some boundary of space is equivalent to a theory with gravity, a quantum theory with gravity inside that boundary, so-called bulk. So basically, in some abstract sense, the idea is that a theory without gravity, just a quantum mechanical theory, could be a theory of a quantum computer, is equivalent to a theory with gravity in one higher dimension. And now, this is still a conjecture, but there is a lot of interest and evidence for this conjecture being, has some relation with reality. Or things that we know about gravity and things that we know about quantum mechanics. So, so the interesting question is that can we build quantum black holes on a chip, for example? We can make smartphones. Can we make a smart holes? That's one of the names I came up during this conference, I guess. Maybe for me, at least, that would be a big legacy that we have. So in fact, there are ideas of building things like black holes on Earth. So Bill Unruh calls them dumb holes. The idea is that if there's like something is moving very, very fast, faster than the speed of sound, then it makes something like a horizon of a black hole. So he calls them dumb holes because it means you cannot hear things that are, you cannot hear them basically. But I want to have a smart holes, not dumb holes. And the smart holes, ones that actually share the same quantum properties, they have the same entropy as a black hole. That's a smart hole. And can we build, same way we can make a smartphone, can we make a smart hole?
Another problem that has vexed physicists is whether black holes destroy information, with relativity seemingly saying they do, and quantum theory seemingly saying they don't.
Black holes, they form from the collapse of stars or the mergers or binary mergers, which we've heard a lot about in this conference. And information can certainly fall into a black hole. You can take your diary and throw it into a black hole. Usually we think of quantum information as being thrown into a black hole, some qubit system. And according to quantum mechanics, information can't be destroyed. And so we find that information has to come out of a black hole. General relativity, however, seems to predict that black holes just can destroy information completely. Now you might say black holes seem like a pretty extreme regime, not one that we've actually tested. But as it turns out, the information paradox manifests already when the black hole is pretty big. And if you look at the event horizon of a very large black hole, the effects of general relativity are actually pretty small at the event horizon of a large black hole. And the reason for that is that the larger the black hole is, the sort of further away the event horizon is from the singularity of the black hole, which is where all of the crazy stuff is concentrated. So if you just look at the event horizon of a sufficiently large black hole, it kind of looks like our solar system we expect, where we don't see a problem with quantum mechanics and general relativity. But already there, we can see that if information is going to be conserved through the evolution of black holes, then we are going to have to somehow violate general relativity on these scales. So you could ask, okay, so what's really happening here? Somehow the information has to be transported outside of the black hole, and that requires something very different from what we've seen so far, because it means that information can sort of propagate faster than the speed of light, and across vast distances in space, and also essentially instantaneously. And you could ask, if that's happening for a black hole where the gravitational effects are not very strong, they're similar to what's happening, say, between Mercury and the Sun, why haven't we already seen that? We have certainly not seen evidence that that can be true. So one of the resolutions, I would say the resolution that I'm a proponent of, suggests that this does happen. But in order to observe this happening, you have to have you have to be able to do extremely complex measurements. And when I say extremely complex measurements, I mean measurements that are exponentially complex in the amount of information that sits in a black hole, which for solar mass black hole is, I think, something like 10 to the 70. So this is a tremendously complex measurement. And so we haven't seen this type of superluminal communication because we have not made the measurements that need to be made in order to observe such crazy phenomena. And you might say, you pulled that out of a hat. That seems ridiculous. You just said, oh, sure, it happens, but we haven't measured it yet because it's too hard. But the thing is, the consequences you get by saying that that is something that happens, by suggesting that this is how the problem gets resolved, as a consequence, you're able to reproduce all of the calculations that sort of came before that resolution. The calculation within some classical general relativity that showed us information is conserved. You can reproduce that calculation. You can reproduce various other things that are true of black holes and black holes that evaporate. And so it seems that it can't just be a coincidence that we put in this ingredient and everything else kind of follows in a very consistent fashion. Basically, what I'm saying is that the principles of general relativity, light is the fastest thing you can have and various other things, those break down. And you would see violations of general relativity if you were able to make measurements of that level of complexity.
But if you can travel faster than light, what happens to causality?
So you would be able to violate causality in this. But again, the way that you would violate causality is very controlled, because it's the measurements that you're making. These are measurements about about observable quantities that are extremely high complexity. And the parameter that controls how complex they are is the parameter that also controls sort of the quantum gravity coupling. So these are quantities that in some sense should not be governed by general relativity anyways. And so it's not, I don't find it that, I mean, it is strange, but I don't find it so disturbing that quantities that are so complex in this parameter, which really belongs in quantum gravity, that those quantities behave in ways that can violate basic constructs within general relativity.
Of course, this is only one way to resolve the information paradox. For a view that there is no paradox, see our film with Roger Penrose, Bill Unruh, and Bob Wald. You'll find that in the link below.
So not everybody thinks the information is preserved. The people who do just normal semi-classical gravity, they would even argue that it could get lost. Some people would argue that if they have nothing else in the theory to bring the information out, information is lost. Some people with the same semi-classical gravity but no extra features say is trapped inside a baby universe. And some people with loop quantum gravity would say is trapped for a long time and then leaks out very, very slowly, which is not the same as coming out in Hawking radiation. It just leaks out very, very slowly. That's the answer from loop quantum gravity. In string theory, it radiates like a normal body. It's just not a black hole at all. It's just like a normal body, like a string star, just like any other star, and the information comes out in the radiation. So at least now everybody has an answer to what their theory of gravity says about the black hole. The answers are not the same, but everybody's happy to agree that the answers that other people give are consistent with their theory. And I think that's a good state of affairs.
If there is a way for black holes to communicate with the outside, maybe through quantum effects, then they're not really that dark or black, so they're not bottomless pits, as one would get from the classical picture where things fall in but never get out. But there could be a reflection. Basically, at some point you hit the bottom of the pit, and then whatever waves that could get out would get out eventually. And there would be a time scale for it. And that phenomenon, we call them black hole echoes. And in particular, we hope to be able to see them in gravitational waves, because gravitational waves are the only kind of waves that can propagate freely in the space-time of black holes.
If black hole echoes are ever confirmed, it could show there is no singularity inside a black hole. But resolving the singularity is no easy task.
Singularity is not a physical object, it's a breakdown of the theory. You need something else, and normally the conjecture is that you need quantum gravity to describe it. Or in some cases you have that quantum gravity induce a modification of general relativity. There are extra terms that are justified by quantum gravitational correction, for example, that have to smooth out the singularity, because you expect that you have a predictability that in a sense that is just a background of GR, not in general of physics. If you want this resolution of the singularity to happen in a finite time and space, basically you have very few options. One option is that you have a black hole which has an outer horizon. That means there is the usual horizon that you would expect in a standard black hole, but inside you have an inner horizon, where basically the region where the light is trapped is confined, and then you have a core, which in jargon is called a space-time which is very often maximally symmetric. Our solution were even more exotic. Inside the outer horizon you have a wormhole mouth, so you reach a minimum radius and then you expand again, and on the other side you have another black hole structure. These are more exotic, but in principle are one of the possible resolutions. And now you can start trying to understand what kind of different properties this family of solution will have. We have a lot of calculation in quantum gravity models, which are falling very often in the first category, I say, because we are not able really to describe the formation of wormhole mouth. But the first category comes out very naturally in several models, and in this generic classification you see that is one of the resolutions you can have. And this category can also give rise to bounces, black hole to white hole transition, and basically a special case of this category.
And I think the main problem in theory of black holes is that there is no theoretical guidance. So we can kind of keep observing things, but our theoretical guidance is like a 100-year-old theory of Einstein, which we know is lacking quantum mechanics. So I think without a quantum theory of gravity, it's like experimenters are flying blind, so they may get lucky, but in terms of making kind of headway with fundamental physics, I think we need a theoretical guidance.
The two leading candidates for quantum gravity are string theory and loop quantum gravity. So what happens in these scenarios?
Loop quantum gravity is an approach to unify general relativity with quantum mechanics. And this approach sort of in some ways is more starts with general relativity as being more important, and taking the idea that, well, in general relativity, gravity is encoded in the very geometry of space-time, and therefore quantum gravity, which will need quantum geometry as well. There are two elements which are taken very strongly have been taken very strongly by the community, which are rejected. The first is the notion of event horizon. And even in this conference, there is an interesting dichotomy. There are some people who have worked on black hole evaporation for a long time, and to them, event horizon and the presence of singularity seems sacrosanct. They seem like it is there. And then Hawking evaporation will happen, but then space-time still has a singularity, and there's still an event horizon. And that is kind of the basic paradigm that one has in mind. And once one has that paradigm, one gets stuck with some questions, like information cannot come out of the event horizon. So, what happens? So, information is definitely lost, or maybe there's a baby universe, and so on. Or there is a singularity. So, well, singularity is going to soak up information. So, of course, it's not going to be recovered in our universe. Now, in loop quantum gravity, because of quantum geometry, the singularities actually are regularized. In other words, they're resolved. The curvature of space-time can be very, very high, but it doesn't become infinite.
String theory is a theory of quantum gravity. So now we take into account quantum effects. And then if you start looking at this problem afresh, you find that once matter gets sufficiently dense, it doesn't actually keep shrinking under its gravity. At some point, all this matter just keeps fluffing up due to quantum gravity effects into a ball, which we call a fuzzball. And the ball is just slightly larger than the horizon would have been, so there is actually no boundary from which light cannot escape. And this is what gets rid of Hawking's information paradox. I'm very excited about the observations of rotating black holes, and you can look at the accretion disk and its imaging. It's a few years down the road. Or you could look at the behavior of gravitational waves coming out of rotating black holes when they merge. But the key point is this: if you have a spherical black hole, then whether the black hole is empty inside or there is a fuzzball structure inside, once you go a little bit outside the black hole, it actually all looks the same, because there's a general result that outside a spherical body, the whole geometry has to look the same as it would for a black hole. But the same is not true for rotating objects. So the rotating black hole has a certain kind of structure outside the horizon. But if you have a rotating body, which has got some other structure inside the horizon, then outside this horizon, it could have different kinds of shapes. And that could be picked up in these observations of black holes. And so if we do pick up a difference outside, that the geometry there outside is different from the geometry you expect for a black hole, it would immediately tell us that what we have inside is something which is not the vacuum we expect from a classical black hole. And that would be a fantastic signal of the fact that we have seen something from quantum gravity changing the complete structure of the black hole.
All our detectors are very far away from black holes, but we can test some of the predictions of classical general relativity. For example, does the black hole area increase when they dynamically interact with the environment? We can test whether, again, the sound of black holes is the sound predicted by Einstein's theory. And perhaps, just perhaps, in 10 or 20 years, some surprise will come up. We will see that we are not observing what general relativity predicts. Who knows? I think periodically we pass through the stage of thinking, that's it, we've seen all there is to know, there's nothing else we can find, only to get revolutions, right? This comes out periodically. So who knows, maybe 10 years from now, we're going to be seeing the universe much, much better than we are seeing it right now. In the 2030s, when LISA, the space-based telescope, flies. So who knows, I'm crossing my fingers.